Later studies and experiments based on these observations conclusively proved that this was a nuclear phenomenon known as radioactivity exhibited by some elements having unstable nuclei. Unstable nuclei can attain stability by emitting particles. A nuclear phenomenon in which an unstable nucleus undergoes decay is called radioactive decay. In nature, a radioactive nucleus can decay by three modes, namely the alpha decay, the beta decay, and the gamma decay. In alpha decay, a radioactive nucleus emits a helium nucleus, which is referred to as an alpha particle. In beta decay, a radioactive nucleus emits either an electron or a positron. A positron is a positively charged particle with mass same as that of an electron and magnitude of charge also exactly same as that on an electron. If an unstable nucleus releases an electron along with an antineutrino, it undergoes a beta minus decay. If it releases a positron along with a neutrino, it undergoes a beta plus decay. In gamma decay, the radioactive nucleus emits high-energy photon. A detailed study of alpha decay, beta decay, and gamma decay will be taken up later. Let us first derive a relation for the rate of radioactive decay. For this, let us consider a sample of a radioactive element containing n number of radioactive atoms at time t. The number of nuclei, Dn, which will decay, will be proportional to n. Since the more the n value, more will decay in the time interval dt. The number of nuclei that will decay will also be proportional to the time interval dt. If we take a longer dt into consideration, then more nuclei will decay in this longer interval dt, since longer the interval, greater the chance of decaying. Thus, dn will be proportional to n dt. Or, we can say dn will be equal to minus lambda n dt. Here, lambda is a constant of proportionality and is called the decay constant or disintegration constant. Negative sign shows decay of nuclei. This implies that dn by dt is equal to minus lambda n. Let this be equation 1. This can also be written as dn by n is equal to minus lambda dt. Let this be equation 2. Integrating equation 2, we get integral dn by n in the limits n naught to n is equal to minus lambda integral dt in the limits t naught to t. Here, n naught is the initial number of nuclei at time t naught, and n is the number of nuclei at a later time t. Evaluating the integral, we get log n to the base e minus log n naught to the base e is equal to minus lambda t minus t naught. If we take the initial time t naught as 0, we get log n by n naught to the base e is equal to minus lambda t. This can also be written as n is equal to n naught e to the power of minus lambda t. This equation is called the law of radioactive decay. Let this be equation 3. The period of time taken by a substance undergoing decay to decrease by half is known as half-life period. It is the time interval for which both n and r are reduced to half of their initial values. Half-life period is denoted by T half.